Are you ready to have some fun deriving the equation now?
NANI?
I bet you do. As I always say, whenever you have an equation in physics, it's either being defined or being derived. For the equation that are being defined, you can't say much about it because it is defined that way. But because of how we define the stuff, then we can use them to derive some new equations. And so here there are 5 equations that you need to learn in this chapter that include work done equals to force times the distance moved in the direction of force. Another equation that is gravitational potential energy, we call it GPE, equal to mgh, mass times gravity, that is the gravitational field strength or gravitational acceleration, which is 9.81 as you learn for the Earth's surface. Height will be the h. That will be the second equation. The third equation that you will get to learn is kinetic energy, Ke, equals to half mv squared, mass and velocity squared. The fourth equation that you need to use would be power equals to energy over time, and the last equation is also power but equal to force times velocity. And so let me talk about the first equation very quickly. That is work done equals to F times d. First of all, this equation is being defined, is definition. So there isn't much you can say, oh, how do we get this? We cannot, because this is being defined. More precisely, when you learn integration in the future, calculus in the future, then work done is more precisely defined as integrating the force with respect to the distance s, let's say. So this is a more precise definition, but for now, in IGCSE, you can just stick with what we put down here, F times d. Or more precisely, in between these two, you can say F times d times cosine theta. And that is because, as we said, it has to be in the direction of force for the displacement. Let me give you an example. So let's say you have a box and it is pulled by a certain tension of, say, 5 Newton, and then the box will move for, say, 2 meters, and you can see that the direction of the tension right here and the direction of displacement horizontally, they are not parallel, and therefore the work done that are really useful, or you may say the force that are really useful contributing energy to the box will only be the one that is in the same direction, that is also horizontal. And that's why there's an angle theta, let's say, from the direction of the tension towards the horizontal direction. And so in this case, then the work done would then be F times d cosine theta, because according to what you learned about trigonometry, that if this is a tension T, then the horizontal one, this one, would be T cosine theta. And let's say theta here is 30 degrees, then what you can have for work done in this example would be 5 times 2 times cosine 30 degrees, and that will be about 8.66 joule, which is the unit of energy for this example. Of course, in most of the cases in IGCSE, there's no angle, so you don't have to worry about that. They are usually parallel. And so in that case, you can imagine that this cosine theta, the angle is actually 0. So if you think about cosine 0 degree, it's actually 1. If you don't know, try to press cosine 0 on your calculator, then you'll find out it is 1. And so that means you can simply ignore it if they are parallel. So simply using the equation here, F times d, will be good enough. And this will be the equation that you need to derive the next 2 equations GPE and also KE. So let me give you some brief idea about how you can apply this equation first. So for GPE, as you know, it is when an object go higher, all right, away from the ground, and it will gain GPE. So simply the mass is the mass of the object, and G is the gravitational acceleration of the Earth or whatever planet you are, and lastly H is the distance that you have gone through. Okay, so by calculating these three multiplied together, then that is the value of GPE that you have. Okay, so later on I want you to derive, thinking about maybe using the work done definition, how to derive this equation. Secondly, that will be the kinetic energy equation. So it's simply as if you have an object that is moving, it could be anything, a car, a tiger, a cat, anything, a person. As long as they have mass and they are moving with non-zero velocity, of course, then you just substitute into the equation and you'll find the value of kinetic energy simply. Okay, so now I would like you to pause the video, try to use the work done equation to derive these two, GPE and KE equation. Try it yourself now.
2,000 years later.
The first one is very simple for GPE. Again, remember you have to use the definition, the work done equation. Work done equals to FD to derive the new equation, GPE and KE. So here, think about this. In the scenario, you have an object, and that object will have a mass m on whatever planet surface. It will have definitely weight, which equals to mg. And for this is something that we learned in the previous chapter. And so if you want to lift it up for a certain height, then you will need a force that is equal in magnitude of the weight to go against it for sure. And so in this case, if you have gone through a certain height, let's say h, then that is the displacement you have. And so now it should become very obvious to you. So by applying the equation work done means the energy that you put in to do something. So force times distance, let's just recall the general equation first. And then the force here would then be the weight W, and the D here will be the height. More precisely, if you like to put delta H, that will be even better. And so the next step is simply changing W into mg, and so you will have mg delta H, and that will be the work done you need to lift up a certain object through a certain height. And that is exactly the same energy as we call GPE and the equation mgh. The h is actually the height change instead of just the height. Next, for kinetic energy is more challenging. So if you haven't worked it out, here is a hint for you, and if you like, you can pause anytime in the video and try harder yourself. Again, this is quite fun if you try to derive it yourself instead of just listen to my answer. So again, what you have to think about is, think about the scenario. So let's say you have an object, let's say a ball, which was having an initial speed or initial velocity to be 0. And now what you do is you applied a force to it. And of course it will accelerate, and eventually it will gain certain speed. So let's say v is the final velocity as you learn. And it has gone through a certain distance as well. So let's say this is distance d. So this is a scenario, and you can try to apply this and think about it if you haven't derived it. So pause again if you haven't done it yet.
A few moments later.
Okay, so think about this. You have to again start with the basic definition. So work done, simply. Work done is like the mother of the equation in energy. So force times the distance, and as you can see, they are parallel, so you don't have to take the cosine theta. the force here should equal to the net force. Actually, I should write, lowercase f. But then eventually applying the idea of Newton's second law that you learned earlier, then you know it would equal to ma. Okay, and d is the distance that it moved. It will equal to the average velocity. So when you say average velocity, it's not initial and it is not final. It's actually the velocity at the middle, right? And so what I can say is it is v minus u divided by 2 because it's like the middle. I mean, if v final velocity is 10, then the middle is like 5 because from 0 to 10, the middle is like 5. It will be the average velocity. So so that's why it is v minus u divided by 2 will be the average velocity. But then we have to multiply it with the time it takes. So let's say time is t, so then we can find the d. Okay, so make it easier for you to read. This is d, and f will be the one that is ma. And so moving forward, then we will have m and a according to what again you have learned about acceleration definition would then be again v minus u divided by t because change of velocity over change of time. And so obviously this t and that t would eventually cancel out. Like so. And let's not to forget the u is actually 0 here. So both of these u will become 0. So eventually if you look at what are remaining, then that is basically half mv squared. And so that is the equation. Trust me, you use it very often this year and also if you study IB physics. Now here is a side question for you. It asks you, well, we all know that the units of energy is joule, which is again definition. Can you try to write other forms of unit instead of joule? Again, the way that you can do it is by looking at the equation itself simply. So pause the video and try it yourself. Okay, let me show you how I would do it. So first of all, you have new 3 equations, and each of them, the whole thing, will have an equation of joule, that is energy. And so that means you can say joule would equal to whatever the units that you can find from those equations. That the first one, work done, will be force times distance. So that is force will be Newton, distance will be meter. So this could also be equivalent to joule. Next, for GPE, then you will have mass, which is kg, and then g will be the one that you use for acceleration. If you remember gravitational acceleration, so you can use probably meter per second square, and so maybe it's better if you use ms negative 2, and then height is also meter, so we can use m square. In this case, meter square. So that will be equivalent to joule as well. Of course, that should also be equivalent to Newton meter. And lastly, for kd, you can do the same thing. The half, 1/2, it has no unit. You can ignore it. And then for m, it will be kg. And for v, it is meter per second, ms negative 1. And then because it's square, so you have m square and s negative 2, which is the same as the one that you find. So that means this one is kind of redundant in this case. So only 3 kind of versions. So if you really don't remember, although it's hard, if you really don't remember that unit is joule, then you can use the other 2 alternatives in the exam. Let's talk about the next 2 questions about power. So again, for the first equation, power equals to energy over time. This, as you can see, is by definition. So we can't argue much, we can't discuss much. It's simply the definition. And the unit is watt, W, okay? And the only equation that you can derive right now, I want you to derive right now, is P power equal to F times V. Let me give you the context. Let's say you have, say, a car that is moving forward with velocity v. This v is the same as this velocity v. And when a car is moving forward, maybe there is some sort of friction or air resistance. So let's say there's air resistance that is trying to decelerate, try to drag you backward. But then for the car itself, you have a forward force from the engine, which is transferred by the tire, etc. So a forward force simply that is pushing the car forward. So since, as I said here, you are maintaining its velocity, and so that means the force, forward force, and the air resistance, the backward force, will be equal, so that your acceleration will be 0. So using this context, can you try to derive this equation, P equals to F times V? Pause the video and try it yourself.
A few moments later.
Let me show you how you can do it. It's very, very simple. You just have to use the definition always. So the definition of power, as we said, is energy E over time. And the energy here, you can also refer as the most fundamental form of energy, which is work done, that we have learned earlier. So let's put down W. And work done would equal to force times the distance, and here, since the force and the displacement is in the same direction, parallel, and so we don't have to take the cosine if you're wondering. And basically this is the answer. If you look at the equation this way, d over t, that is simply velocity, right, according to how we understand velocity. And so that will simply be how you can derive the equation. Of course, for the assumptions, again, you will have the force being parallel. Okay, this is simple for myself, it's not official, but then you can use this notation as well for your own note. Force being parallel to the velocity, this is one assumption. Otherwise, you need to take the cosine theta, like we said earlier. Second point, actually, if you have to make more precisely, then V is constant. Alright, so you are not gaining any speed, because if you gain speed, then basically it means that you are gaining kinetic energy. Then the equation will be different in this case. Lastly, similar to the previous section, try to find an alternative form of unit instead of watt. Try yourself and pause the video now.
A few moments later.
So like previous, we can say work done equals to the equation that you could see, which is, well, actually we should do E over T first. So it's joule per second, or you can write J as -1, or you can look at FV, so which is Newton meter per second. And in fact, if you look up what you did earlier, that basically is the one that you write for joule and Newton meter, and you just add as -1. So obviously you can do the same for the alternative format, which is kgm square. Let me copy it, kgm meter square, and then s -2, but this time you should have one more negative, so -3 here instead. So in this video, you have learned about 5 Newton's equations. The first one is work done equals to force times displacement. The second equation is GP equals to mgh. The third equation is KE equals to half mv squared. And the fourth one is power equals to energy over time. And last one is power equals to F times V. You are expected to remember and recall them in the future, no matter we are doing homework or doing the exam paper. I also hope you enjoy deriving the equation, because this should be the most interesting part of studying physics. I hope to see you again in the next video. Please make sure you like and subscribe to this channel. I'll see you again next time. Bye.